Hi, this is John Whitaker for the Probability Graduate Level class, and this is our, I believe, our 9th video lecture. And today I want to concentrate on one particular famous continuous random variable, and that is a normally distributed random variable, and that's pretty much exclusively what we're going to look at today. There will be a few facts about expected values of random variables in general, and maybe something having to do with the relationship between the CDF and PDF, but mainly today is about the normally distributed random variable. Well, as we get started, we should say, what is a normally distributed random variable? And so here's its definition. A continuous random variable X is said to be normally distributed with parameters U and sigma squared. And here, when I say sigma squared, sigma is greater than 0. If the PDF of X, probability density function, is f of X equal to 1 over the square root of 2 pi, and the denominator is sigma, then there's e to the minus quantity x minus mu to b squared all over 2 sigma squared. That whole fraction is the exponent, where x is an element of all. So this is defined over the whole real number. And it's that bell-shaped curve you might have seen before. That's what the PDF is of this normally distributed random variable. Okay. Well, the first thing we want to notice is that we want to consider the integral of 1 over the square root of 2 pi. Well, let's first of all just look at this integral, okay? E to the minus x squared over 2 dx, and we'll look at the minus infinity to infinity. Just look at this. Okay. First of all, this is not a function for which we have a closed form for the antiderivative. So we can't easily use the fundamental theorem of calculus to try to compute this. So instead, what we'll do is we'll have this. To compute this integral, what we'll do is we'll note that this guy right here, e to the minus x squared over 2 dx, if you were to square it, that's really the same thing, if you wanted to write it, e to the minus infinity e to the minus x squared over 2 dx times itself, but instead of writing it exactly the same, what I'll do is I'll say, just with the different variables, e to the minus y squared over 2 dy. Symbolically they're the same, this answer is the same as this answer, we're multiplying together, this is the square. But I'll rewrite this as a iterated double integral. Minus infinity, minus infinity, minus infinity, minus infinity of e to the minus x squared over 2 times e to the minus y squared over 2, and then dx dy. And that's the same thing as the double integral, minus infinity to infinity, minus infinity to infinity, of e to the minus quantity x plus y, or x squared plus y squared, over 2 dx dy. So that's what we have. Now, what I'm going to do is do a change to polar coordinates. So this becomes the integral from 0 to 2 pi from 0 to infinity of e to the minus, this would be r squared over 2, and then this is r dr d theta. So that's the change that we would have using polar coordinates. Okay. Now, to integrate this first part, we have e to the something here. The derivative of the something is minus 2r over 2, which is just minus r. So I need a minus sign to be able to integrate that. So really I'll rewrite this from 0 to 2 pi, integral, so I'll put a minus 1 here to compensate for the minus 1 I'm going to put. So I can do the inner integral now. And that's equal to the integral from 0 to 2, oh gosh, equal to the integral from 0 to 2 pi. That inner integral, I can find an antiderivative for it. It's e, or it has a minus out front of it, to the minus r squared over 2, evaluated from, I think, evaluated from 0 to infinity, d theta. Okay. So when I stick in, I know this is supposed to be an improper integral. We think of r getting really huge. E to the minus really huge number divided by 2 is e to the minus huge number, huge positive number. And that goes to 0. So it's really equal to the integral from 0 to 2 pi of 0 minus a minus using the fundamental trig calculus. So plus what I get when I stick in 0 for r. So that's e to the 0. And then d theta. So that ends up being the integral from 0 to 2 pi of 1 d theta. All right, well, this is an easy integral. So the integral of 1 d variable is just the variable, so this is equal to theta, evaluated from 0 to 2 pi, the fundamental trig calculus, so we get 2 pi. So what I just found is that the integral of e to the minus x squared over 2 dx. So I had this guy being squared. So this guy is equal to the square root of 2 pi. And so here, it's really supposed to be plus or minus, but we know that this is a positive function that we're integrating from minus infinity to infinity, so our answer's got to be positive. So what that says is that, well, I'll leave that alone. That's what we have. Okay. Now, well, I guess I could write this down. So just 1 over the square root of 2 pi, integral from minus infinity to infinity, of e to the minus x squared over 2 dx is equal to the 1. Okay, well that's close to what we're wanting to show is equal to 1. Remember, we want to integrate the PDF of a normally distributed random variable parameters mu and sigma squared and get 1. So let's take a look at that integral. And it will relate to the integral we just had. We just have at the bottom. So, 1 over the square root of 2 pi times sigma in the bottom, integral from minus infinity to infinity of e to the minus quantity x minus mu to b squared over 2 sigma squared dx. So here's what we're going to do. We're going to let y, or let u, equal to x minus mu over sigma. Then du will be equal to 1 over sigma dx. Okay? So this 1 over sigma that's outside, I'll put it inside. And this part becomes 1 over the square root of 2 pi. Our integral
as x, the limits of integration, as x goes from minus infinity, well, u would be minus infinity. And if x was a huge positive number, u would still be a huge positive number. The sigma squared can be brought into x minus mu over sigma, all that to b squared. That would be what we have here. So this is e to the minus u squared over 2. This 1 over sigma I bring in with the dx, and that's d. And we just looked at this quantity just a second on the other side of the board where we had the variable being x, but it's the same interval, and we found that to be equal to 1. So that's what we have. Thus, the integral minus infinity to infinity of f of x dx equal to 1, where f of x is the PDF of a normally distributed random variable. Okay. And of course, we want to eventually get to the expected value of the normally distributed random variable, and we will, as well as its variance, and we will. But we're going to do a little bit of work before that. Okay. As a fact, if x is a continuous random variable, with CDF, cumulative distribution function, big F of x, and then the derivative with respect to x of f of x, big F of x, is equal to little f of x, where little f of x is the probability density function of x. That's a fact, and it stems, as you'll see in just a second, from the fundamental theorem of calculus. So proof. So a little left. F of x be the CDF of a continuous random variable x. Then, if we take the derivative, well, I'm sorry, then let's remember what the definition of the CDF is. So, f of x is equal to the probability that big X is less than or equal to x, which is equal to the integral from minus infinity to x of f of t dt, where little f of t is the p of x. And so, the derivative with respect to x of f of x is nothing more than the derivative with respect to x. The integral from minus infinity to x of f of t dt. Now, by the fundamental theorem of calculus, this is equal to the inner function evaluated at x times the derivative of x, which is just 1. Okay? And this is by the fundamental, a version of the fundamental theorem of calculus. So that proves what we were looking to prove. Here's a fact. if x is normally distributed with parameters mu and sigma squared, then y equaling to ax plus b, so that function of x, that y is a random variable now. Is normally distributed, so it is a normal random variable, so y is. With parameters so its parameters, let's see, I think are, just a second, it's b, so it's a times mu plus b, and a squared sigma squared. So that's what we want to prove. All right, that's accurate. Let's do a proof. So we'll let x be normal with parameters mu and sigma squared. Consider y equal to ax plus b. Now what I'm going to do is I'm going to look at the CDF of y. So note the CDF of y, cumulative distribution of y. I'm going to call it big F sub y of x. What's that equal to? That's nothing more than the probability that y is less than or equal to x. And that's equal to the probability that a times x plus b is less than or equal to little x. Let's concentrate on that. Okay, that's equal to, solving for x, is equal to probability that ax is less than or equal to x plus b. Should be minus b. All right, now, let's consider two cases. So here's case one. A is greater than, A is greater than 0. So here, one thing we need to say is that A can't be equal to 0. So A is different from 0 in our fact. I didn't say that. But if A is bigger than 0, this is equal to the probability that x is less than or equal to x minus b over A. And that's equal to big F of x, the CD of x, evaluated x minus b over A. So, if you take the derivative with respect to x of f sub y of x, that's going to be equal to the derivative with respect to x of f sub x of x minus b over a. Well, this is nothing more than the PDF of y, evaluated x, which is going to be equal to here f sub x of x minus b over a, and then you have to, by the fundamental theorem, no, by the chain rule, I should say, in our previous fact, you'd have to multiply this by the derivative of the inside here, which is 1 over a. So f sub y of x is equal to, well, what is this? This is 1 over the square root of 2 pi, so I'm writing down the PDF of x, times sigma in the bottom. Here I have e to the minus, it would be, and then I have this a, 1 over a, I have to say it would be e to the minus x minus b over a, minus mu to b squared all over 2 sigma squared. That's the exponent. Okay? So that's my f sub y of x. So in this fact, again, we can't have a being 0. Now, that gives us f sub y of y is equal to 1 over the square root of 2 pi, and here is sigma times a, or a times sigma. E to the minus, you get a common denominator, so I'm going to take just a second. So it's x minus b all over a minus, well, it would be mu times a over a to b squared all over 2 sigma squared, which we can rewrite as 1 over the square root of 2 pi a times sigma e to the minus quantity here. This would be x minus, I'll write this down as the quantity, mu, a times mu plus b, that's what that is, to b squared, that's at top. The bottom will be a, you have to square it, so I'm going to put it in the bottom as 2 sigma squared a squared. Now when you look at this form, that's f sub y of y. I'm sorry, of x. I said the wrong thing. When you look at this function, it is the form of a PDF of a normally distributed random variable whose parameters are a times mu plus b and sigma squared a squared. And that's exactly what we want. So it's normally distributed with parameters a times mu plus b and sigma squared a squared, where sigma times a is greater than 0. Now we had another case. That was case 2, and that's where a is less than 0. So in this case, what we have is that f, I think big F sub y of x, from where our previous work was, that's equal to the probability that ax is, it was less than or equal to, it was less than or equal to x minus b. That's where we were. And now I'm going to divide, like I did before, both sides by a, but I'm going to switch the inequality because a is a negative number. Okay, so that's equal to the probability that x is greater than or equal to x minus b over x. Well, that's equal to 1 minus the probability that x is less than or equal to x minus b over x. So, well, I'll say that's equal to 1 minus f sub x, the CDF of that, x random variable. Evaluate x minus b over a. So f sub y of x equals to, in this case, 1 minus f sub x of x minus b over a. So the derivative with respect to x of both sides of f sub y of x equals the derivative with respect to x of this quantity. Derivative of 1 is nothing. The derivative of this guy, well, it's got minus in front of it. This guy's f sub y of x. So this equals to minus little f sub x, the c here, x minus b over a, again, times 1 over a. So let's expand that. So that gives us the f sub y of x, in this case, is equal to minus 1 over the square root of 2 pi sigma. Sigma's not underneath. Then I have 1 over a, so I just put a down here. I have e to the minus x minus b over a minus mu all over 2 sigma squared. That's what I have as a function. This I'll rewrite as 1 over the square root of 2 pi sigma times minus a. Now a was negative, so minus a is positive. Here, this will be equal to e to the minus quantity. We got a common denominator before. I'm going to rewrite this as we had before, as x minus the quantity a mu plus b to b squared. The a is to b squared, so I'm going to put it in the bottom, 2 sigma squared a squared. Now, this, because a was a negative number, minus a is positive, this is my PDF of y, and if you look at it, it has the exact right form of a PDF of a normally distributed random variable whose parameters are a times mu plus b and sigma squared a squared. So y is normally distributed in this case. With parameters a mu plus b and sigma squared or a squared sigma squared. That's what we have in this case. It's what we had in the previous case. So in all cases, we get the result we want. So that's the proof. Okay, I want to look at a particular normally distributed random variable called a standard normal random variable. And here's its definition. So a continuous random variable is called a Z. Is said to be a standard normal random variable if the PDF of Z is, so it's f, and I'm going to write this down, of Z is equal to 1 over the square root of 2 pi e to the minus z squared over 2 raised to this. So that's what I wanted to write. This really standard normal random variable is a normally distributed random variable whose parameters are 0 and 1. Okay? In this case, I'll write this down. We see the standard norm is a normally distributed random variable with parameters of 0 and 1. So sigma squared is 1, and this is the mu. Okay. It turns out, as a fact, before I go further, we kind of are benefited by looking at standard normal random variable lots of times, because we can prove something by a standard normal, prove something about a standard normally distributed random variable. We can extend that result to all normally distributed random variables. Okay? And so, how can we extend it? We extend it through this fact here. So fact, if Z is a standard normal random variable, then X equal to sigma Z plus mu is normally distributed with parameters mu and sigma squared. So you can create kind of a generic normally distributed random variable through the standard normal, through this type of algebraic combination. The proof of this is based on previous fact. Okay? And so here, if Z is standard normal, then X equal to sigma Z plus mu is normally distributed. This is about a previous fact that we did today. With parameters, okay, I don't know what the parameters are. Oops. Okay, this is by the previous fact, okay? That we had broken up into two cases where A was positive or negative. Okay, remember what you have right above. The parameters, what were they? They were A times mu, wasn't it A times mu plus B? So I'm going to put that in top. Really, here's what it is. Parameters. So it's A. The A in our particular problem is being played by, I'm going to move the camera so we can see both of it, okay? And I'll move the camera back. I think you see. The A, remember we had was AX plus B beforehand in the previous fact. So the A, in our case, is sigma. The mu was the parameter of z, which in this case is 0. Plus b, okay? And b, in our case, for our definition of the algebraic combination, the previous factor is y, here's called x, it's mu. Which equals to mu. And, okay, so here was a squared, sigma squared in our previous fact. So, here, I think you can see a squared, sigma squared. Here, the a squared is sigma squared. The sigma squared was the second parameter from the variable involved in the algebraic combination. That's just 1. So that's what we have. So that's what we have by the previous fact. So x, okay, by the previous fact, is normally distributed with parameters mu and sigma squared. Okay. As another fact, and this is just in general about any random variable. So if x is a random variable, and a and b are real numbers, then the expected value of a times x plus b is equal to a times the expected value of x plus b. This is a fact. I'm going to prove it. I'm going to prove it in two cases. Let x be a random variable and a and b be elements of real numbers. Okay, so here we'll have two cases. So case 1, x is discrete. So I'm proving when x is discrete or x is continuous. Then the expected value of ax plus b, okay, this is the expected value of a function of x. So with a discrete random variable, that's the sum over all possible x values of ax plus b times f of x, which I can break up into the sum, distributing the f of x. Ax times f of x plus b times f of x, which I can break up into two sums, sum over x values of ax f of x plus sum over the x values of b times f of x. The a is a constant, so I'll pull it out of the sum, x f of x plus the b is a constant in the second sum, so I'll pull it out, f of x. And here, this is a, the sum over all x values of x times f of x. Well, that is the definition of the expected value of x. Plus b, and the sum of all the f of x values over output values for big X, little x. That's equal to 1. So this is equal to a times the expected value of x plus b, which is what we wanted to show. And so it's true in the case where x is a discrete random variable. Now, case 2, let's say x is a continuous random variable. Then the expected value of ax plus b, again, this is expected value of a function of x, it's continuous random variable. So it'll be the interval from minus infinity to infinity of ax plus b times f of x dx. Again, I'll distribute the f of x as the interval from minus infinity to infinity of ax times f of x plus b times f of x dx, which we will split up into 2 intervals. So it's the interval from minus infinity to infinity of a times x f of x dx plus the interval from minus infinity to infinity of b times f of x dx. I can pull out the a. I got the interval from minus infinity to infinity of x times f of x dx. You can see the proofs here in both cases are very analogous. I pull out the b from the interval from minus infinity to infinity, interval of f of x dx. That, of course, is equal to a, the interval from minus infinity to infinity of x times f of x dx, nothing more than the expected value of x. Here's b, the interval of the PDF over the whole real line is equal to 1, so b times 1 is just b. So that proves it in the 2 cases that we're interested in. Okay, we will conclude by proving what the expected value is of a normally distributed random variable defined as mu sigma squared, and what is its variance. Those 2 factors. Not much further to go. So here's the fact. If x is normally distributed with parameters mu and sigma squared, then the expected value of x is equal to mu. So here's the proof. I'm going to start off by letting z be the standard norm. Then the expected value of z is equal to 1 over the square root of 2 pi, interval from minus infinity to infinity, z times e to the minus z squared over 2 dz. Here I'm looking at e to the something I'm trying to integrate. It's z times e to the something. I'm looking at e to the something. The derivative of something is minus 2z over 2, which is just minus z. I almost have that. I just need a minus sign here. So imagine putting a minus sign there and compensating for outside of it. What we get is minus 1 over the square root of 2 pi, e to the minus z squared, so it's like e to the u du, over 2, evaluate from minus infinity to infinity. Now look, I didn't write this down as an improper interval, but I could have. If you let z get really, really big and look at e to the minus really, really big thing squared over 2, that goes to 0. And the same thing, sticking minus infinity. So this ends up being minus 1 over the square root of 2 pi. This will be 0 minus 0, which just equals to 0. And you know, that was the mu involved for the standard norm. So the statement's true. X is the standard norm. But we're going to use that. So x then is equal to, it was sigma z plus mu. That's what x is. The standard is the normally distributed with parameters mu and sigma squared. So this is a way of expressing this x. So the expected value of x, well, that's nothing more than the expected value of sigma times z plus mu, which we know to be equal to sigma times the expected value of z plus mu. But I just found the expected value of z was 0. So this is sigma times 0 plus mu, so that's just mu. And so that proves what I wanted to show. So the expected value of the standard normal is mu. Its parameters are mu and sigma squared. Now, as a fact, if x is normally distributed, with parameters mu and sigma squared, then the variance of x equals to sigma squared. Okay, this is the last thing we're going to do. And this is interesting. Okay? What we're about to do here is interesting. Wait, it's done. Okay. So let's start with proof. Make sure that this is clear. It looks a little fuzzy. I'm on into focus. There I am. So proof. So let x be normally distributed with parameters mu and sigma squared. Then, here we're going to use the variance of x, okay, not the formula. This is equal to the expected value of x minus the expected value of x to b squared. Okay, that's what I'm looking at. And that's going to be equal to the integral, well, I'll rewrite this, excuse me, as the expected value of x minus mu to b squared and that is equal to, so by the expected value g of x, this is equal to 1 over the square root of 2 pi. Sigma's in the bottom, integral from minus infinity to infinity, this, so the x minus mu to b squared, e to the minus x minus mu to be squared all over 2 sigma squared dx. So what I want to do is we're going to make a substitution. We're going to let y equal to, so change the variable, x minus mu over sigma. Then dy will be equal to 1 over sigma dx. So this 1 over sigma, I'll group with this dx to make dy. So this ends up being, and the y's will still run from minus infinity to infinity, because x runs from minus infinity. 1 over square root of 2 pi. That sigma that was in the bottom, I'm going to put with the 1 over sigma, I'm going to put with the dx to give me the dy. This would be, well, x minus mu is equal to sigma y. So x minus mu is sigma y to be squared. So it's integral from minus infinity to infinity. Sigma squared y squared. This is e to the minus y squared, the x minus mu over sigma to b squared is what this is. So it's all over 2. This is a 2 here. And then the dy. We're almost done. So that's equal to, I'm going to write 1 over the square root of 2 pi. I'm going to pull out the sigma squared. Integral from minus infinity to infinity of y squared e to the minus y squared over 2 dy. Now I'm going to integrate this by integration by parts, but here's what I'm going to do. I'll let u be y, du will equal to dy. dv is going to be equal to y times e to the minus y squared over 2 dy. The antiderivative of this, so integral this, here's e to the something. The derivative of this something is just minus y, which I almost have. So I need to put a minus associated with y, so I'll put a minus out front. And then it'd be e to the minus y squared over 2. So I have 1 over square root of 2 pi, there's a sigma squared in the top, times, so it's uv, so it's y with a minus here, e to the minus y squared over 2. That way from minus infinity to infinity. Okay, look, I'm doing this informally. I know I should have limits involved, but I'm going to let it go at that. Minus, it's the integral of v du, so here's the minus plus, e to the minus y squared over 2, minus infinity to infinity, dy. That's what we have. This guy turns out to be 0. You'd have to use low-cost rule to get it. So 1 over the square root of 2 pi, sigma squared is sitting here. Gosh, this is 0. Plus, this guy we did earlier to start with almost today, and we found this to be equal to the square root of 2 pi. So this is, here, I'll rewrite this, sigma squared over this. So square 0 plus square, no, sigma squared over the square root of 2 pi times square root of 2 pi equals sigma squared. That's what I wanted to show. Ladies and gentlemen, we just showed that the variance of normally distributed random variables with parameters, mu and sigma squared is sigma squared. That's what I want to conclude with today. Thank you very much for your time and patience.